coil was being rotated, Abby, through the field. And without wasting much time, we have our north, we have our south, we have the field that runs from where? From north to south. And at the end of the day, we have a coil of wire. And this coil of wire is connected to some slip ring and carbon brushes and galvanometer, and you have it like that, like that, like that. So at the end of the day, we saw that when we flipped the coil, we rotate. When we try rotating the coil is going to be cutting through the magnetic field, and we call that magnetic flux change, Abby. And as you are changing flux, current started flowing, and we know how the direction of the current was the last time we did it. Then the current came down. Then we now said that, let's say this place is A, B, C, D. For an AC circuit, this thing will flip over. And when it flips over, the current that went from A to B to C to D will eventually go from D to C to B to A. And that is why we call it an alternator. So it keeps alternating. So they can ask you that what is an alternating current? So it's a type of current that keeps changing direction or keeps alternating periodically. So it keeps changing with time. Then we call it an AC circuit. That's why for an AC circuit, the voltage can vary. You can have something like E naught sine omega t or E naught sine theta and all of those things. So there's a particular peak voltage. There is a particular voltage at a particular time. We call this the instantaneous voltage. We are going to talk about this under AC circuits when you get there. But because this thing keeps flipping, and we said something, that the EMF generated is directly proportional to the change in flux. Abby? And from there we said that E is equal to minus N, the phi, the T. Now, change in flux is directly proportional to E, meaning that as flux is changing, E is also changing. So there's a time that E will be maximum because the flux was maximum. So which means that this E might not really be the maximum value. The E that is the maximum value is what we usually call the peak voltage. Then this one is usually called the instantaneous voltage. Instantaneous voltage. So instantaneous voltage is talking about the value of the EMF at a particular time. As you are rotating it, you are cutting through the flux. And as you are cutting through the flux, flux is changing. Voltage is also changing. So the deflection will start from 0, then it will be increasing. Abby? So it's not like it will just bam. It will keep increasing as you are changing it. Then when you're changing it back again, it will go back again this direction. So you see that this line will keep deflecting to the right, to the back, so it will be increasing. But if it is a DC, it's just one direction. So the moment this thing goes like this, it does not come back like this. So the voltage in DC, that's why when you have been doing electricity, I don't know how far you have gone in current electricity. You would have seen a circuit with resistor, with load, with all of those stories. And all these circuits will be connected to a direct current with the key or switch, Abby, and everything. In this case now, the moment you switch this thing on, the bulb will just glow. But if it is an AC you connect, if you have understanding of this, then what I'm saying in story will be understandable. So if it is an AC you connect, an AC circuit, and the moment you switch it off, on, now as you are switching it on, one thing you will see is that as the current is flowing, this thing will go brighter, then it will go down again, then it will go brighter, so it will keep changing like that. Why? Because current will first flow like this, all of a sudden it will reverse again. And at the end of the day, the voltage keeps changing. And as the voltage is changing, you see the bulb getting low, getting brighter, getting low, getting brighter. Unlike if it's, imagine if I switch this lights on now, this thing will just be bright, which means that what is supplied to most of our bulbs is direct current. What comes from transformer is an alternating current. But in your house, there's a way all of these things are converted. They are rectified. We have what we call rectifier. But your knowledge of all this DC from electricity is what will help us here. But take your time. Some things might sound magical. It's not so hard. Just take your time. So from what we have, I'm going to talk about this later when we get to AC circuit so you understand it. But so far, so good. What I've said here and what I'm saying here, I want to believe you all understand it. We have talked about this. Do you understand this? How we got from A to B to C to D, and how we got from D to C to B to A. You understand that? You might not understand this yet, but to those of you that have basic knowledge, so sometimes when I say some things, you should get my point. So if you see an equation like this equation is saying that you have a voltage at a particular time as you are changing the flux. Then this is the maximum voltage. You have done, what's it called? Waves, Abby. When you do wave, you know you have y is equal to a sine, that's omega t, whatever, Abby. What do you call this guy? Amplitude. That's the maximum displacement, Abby. It's almost like this. Then this one is the displacement at a particular time. So if you look at the wave profile, you are going to have it will be increasing, Abby. Then it will increase to maximum. Then it will be decreasing, and again it's increasing the opposite direction. Then it's decreasing and all of those things. So this place from here to here is where you call the maximum displacement, Abby, which is this part. But at a particular time, you know, we always put y here, and we can put x and as a function of time. So meaning that there's a value for y, but that y maximum is what we call amplitude. So that's the equation. So when you get to AC circuit, we deal with that. Now, let's check how DC works. And you will see that it does not alternate like this. So for DC, you have your magnets, so instead of, let me put it this way, instead of split ring, or what's that one called? Slip ring. You are going to have so let's call this C1, C2, then this is my S1, S2. So let's look at the difference here, A, B, C, and D. Now, when you start rotating this coil, what will happen? Let's rotate it this way. So when you start rotating, the coil will start cutting through the magnetic field, Abby. And at the end of the day, I want to rotate it in this direction, meaning that this is going to come up, Abby. That's the force. Then on this side, it's going to go inside. So in what direction do you think the current will go here? And in what direction will it go here? I'm not trying to waste the marker. So everybody, in what direction will it go on the right side? We have done it before, so don't. And in what direction will it go on the left side? In what direction will current go? Do you still remember your Fleming's right-hand rule? So from your Fleming's right-hand rule, for this now, the force is coming up, Abby, because I'm rotating it this way. So this one is coming up, Abby. Don't worry, we'll soon be through with magnetism. Some of you that just joined the class. because at this stage you join. There are some things we have been talking about, but all the videos are still on YouTube from where we started, so you can go and watch it to catch up. So we will solve questions soon. You will see everything. It's not that. So now, from what we have here, where will the current be going? Is it up or down? Because when you do your Fleming's right hand rule, the force is coming out, Sabi. Then the field is going this way. Then your current is showing up. Do you get that? So that means the current is going to go up. Is that taken? Now, when you get to this side, the force is now going inside. Abi, at the end of the day, when you use your rules again, then the current is going down. So there is no need to waste time on that. Do you understand that? So meaning that the current will continue, it will go down, then it will go this way, then this guy will be deflected. Abi, you don't need to cram it. They can show you all of these things. All you just have to do is apply your rules when you need to apply it. So from what we have here now, this will be deflected to the right. And at the end of the day, your current will go from A to B to C to D. Now, the question now is that what now makes AC different from DC? This split ring that you have, for AC, this one would have flipped. Telebati rotates, normal flip. That's why they call it slip ring. So it will slip over. It will rotate. But for this one will not leave its position. So even if you rotate this coil, this one remains. I hope you're getting the point. That's how it's designed. We are just showing a kind of example for you to see. So it's designed in a way that this one will not what? Will not rotate with it. So only the coil will rotate. Now, let's say the coil is E, F, G, H. Now, when you rotate it the first time, that means E, F will be here, Abi. G and H will now be here, right? So at the end of the day, but this guy will not rotate. So even after that rotation, you do check it again, the current will still go up, Abi, and it will come down. But that current that is coming down will still pass through A, B, C, D, because A, B, C, D did not flip. Can you picture what I'm saying? So A, B, C, D will not flip. And if that does not flip, then the current will still go through A, B, C, D. And that is what you have for a DC circuit. So for a DC, current only goes in one direction. So let's now differentiate between AC and DC. So for an AC, current alternates. Current alternates periodically. So that means for a given time, the current keeps changing with time. So it's going forward and backward and forward and backward. So it keeps changing periodically. Or they can tell you that the current can move in both directions. So, but for DC, currents only move in one direction. Is that taken? For AC, I want to believe you know that the voltage will vary. The voltage will vary. The EMF will vary. Why would the EMF vary? Because you are changing flux, Abi. And as you are changing that flux now, it's going forward and it's flipping back in DC. So it will keep changing. So most times when you see graph for AC, the graph is always like this. The voltage, when you plot the voltage against time, so the voltage will keep increasing with time, get to the maximum. At that maximum, we call it the peak voltage, V0. Then it will start reducing again, then go to zero. Then, so you now have a formula that says that the V is equal to V0 sine theta. And you remember, theta is always equal to omega t. But for DC, we usually have a constant voltage. If you buy a battery now, they'll just tell you it's 12 volts. Now, in this case now, the voltage remains constant, so it's not changing. So if you draw your graph, it will just have a particular value. 6 volts, 3 volts, 10 volts, whatever voltage it is, it's just constant. It does not change. So if you see a graph for DC, this is what you will pick. For AC, this is what you will pick. That one keeps changing with time. Now you will see that it's going from positive side also to negative side. If you are drawing a graph, you will have positive Y, negative Y, Abby. So if I go like this, that means I go through positive direction, negative direction, keeps changing with time. Now, that's why I told you when we were starting this topic that you should please pay attention from the beginning to the end, because some things will be depending on some other things as we are talking about it. If you are a starter, it might still look difficult, but it's not. But just take your time. Just take your time, please. It might, but there's nothing there, because there are a lot of things we have to imagine. We have to think about the 3D and everything. And that's why I told you when we're starting the topic that please pay attention from the beginning. But from what we have said so far, there's still nothing difficult, because you will start saying simple AC circuits. And when you start simple AC circuits, then when they are now telling you that alternating voltage, alternating, you should understand what they are saying at that point. So the next thing we need to know, the symbol for AC is usually like this. So whenever you see that symbol, you are talking about alternating current. Then the symbol for DC is like this. So that's by the way. Now, we have generated EMF. The EMF we have generated now as a particular value. As it generates voltage nisin, and the voltage you have generated, we used a generator. So the question they can ask you here, number one, is that what does your generator do? It converts mechanical energy to electrical energy. How does it? By rotation of a coil in a magnetic field, Abi. And eventually, if you want to determine the direction of the current, how do you determine it? You use Fleming's right-hand rule, Abi. I'm trying to give you a clue to make the things we have talked about. What differentiates an AC from DC? Split ring and slip ring. Another name for split ring is what? Commutator. Abi? Now, if they ask you what are the components of an AC or DC, what is it? What is AC made up of? Armature, permanent magnets, Abi? Carbon brushes. How many carbon brushes do we have? 2. Do you get it? Those are the things that we ask you. Some things might be sounding like it's strange. It's strange. It's not so hard. Is that taking? Just open your mind. You are not an electrician, so I can try. So you might not really understand how it operates. I can tell you how this fan is rotating now, but can you give me a screwdriver to come and fix this fan, and I'll fix it for you? It's not possible now. I can't go to transformer now and work on it, but I can just tell you the principles on how it operates and everything. But it does not mean it until you have some practical experience. That's when some learning becomes interesting. You get? So some of these things we are talking about now, we'll be looking at. Imagine I'm just drawing wire. Some of these things used to get me annoyed too, because we are just drawing wire. We are showing you but I'm not bringing generator and show you coil of wire and show you the magnet. But many of you might have seen all these transformer in some basic electronics before, but it's not for you to complicate. Just be open-minded. Some of you are in letting create minded. Can you only hear me? Whereas it was need that team they move on. So if you now want to go and study elect, you can start dealing with transformers. Go there. if you are not so happy, you hug your transformer. At least you will be happy by that time. So, but just understand the basic things. So now, if I now ask you, what is the purpose of an AC? It is to generate EMF. Abi, what's EMF? Voltage. Voltage that will drive something. You know where we started from? What did Faraday do? Faraday did an experiment, and he noticed that if you are moving a magnet, there will be an EMF generated. Abi, that EMF now, we have to put it to use. So this same thing I've done is what they will do in power station, our NEPA. That's what they will do. So they already have something that they have water that is helping them to drive. That one that I'm saying that you will rotate like this. They have a giant magnet. They have a giant machine that will help them to rotate the magnets and the coil. And if the coil is rotated around the magnet, they will generate EMF. That's why they call it generator company, power generating company. So after they've generated the EMF, the voltage, then they will send it to town. But when they want to send it to town, that's why I said you should have, it's because we want to cover the syllabus altogether. That's why we divided the topics. Actually, there are some topics you must have covered before you do another topic. But the problem is that this topic that I'm doing now, we always do it like the last part of JAMB class. And by that time, we always rush it. And when you get to exam mode, these are the areas you will see questions the most. You will always see questions there. Electricity, magnetism, and the likes. Some of you might be lucky enough that your questions will just be on motion. And some people, their questions will just be on. But one of the funniest things is that most questions around here are always easy for you to get. But those ones that you call motion, you might think you have gotten the right answer when you solve, and you will not know that you have missed it because you did not use the time appropriately. Or they said then calculate when it is changing time, and you really did not know what they are saying. But most of these ones now, what do they want to ask you here now? And what's the difference between CDC? You pick your answer, except you make mistake. So these questions around here can still be direct at times. But you have 40 questions. Some of me, current electricity. If you have done current electricity, if you have done current electricity well, you would have known how electricity is transferred in communities. Abi, then you will know what we call power transmission. We call it transmission of power. Then it will come from power station to the community. So there's something that what NEPA wants to send. There's a place they used to generate light that the whole of Ibadan will use. Now they want to send it to communities. Before that light gets to the communities, there are some problems they have to avoid. Then we have what we call high tension transmission. So we have to increase the voltage generated by this generator. The voltage might not be that high, and they want to send it to the whole town. So what they will do is they will use a transformer. So after generating that voltage, they will now increase that voltage using another machine. That machine is a transformer. But that voltage is so high that there's a reason they have to make it so high. So they will send it to community. But when it gets to the front of this place now, anywhere there's transformer in our community, there's another transformer. In your street, you would have seen a transformer before, Abi. Now, when you get to your community, that transformer that you always see around your house, the purpose is that before the electricity enters your house, before you start using it, that one will help you step it down. Because what is coming from power station, it's from 20 to 30 to 50,000 kilovolts. It's very, very high. What you are getting in your house is just like 220 volts, 240 volts. That's what is making all of these things work. And at the end of the day, that one will step down all those long, heavy voltage. It will help you to step it down, then send it to your house, and you make use of it. So now, that is the purpose of a transformer. So if they ask you, how did you generate the voltage? You generate it using what? An AC circuit or an AC generator. Now, that voltage you have generated, if it is too small, you want to increase it. If it is too large, you want to decrease it, then you have transformer. Do you get that? So transformer just helps you to transform your alternating voltage, to step it up or to step it down. So transformer helps, this is all you just now need to know, helps to step up or step down voltages. Let me put it in a simple term. Potential difference, EMF, all of those things, they are talking about voltage. So your transformer has two parts. The working principle. How does transformer works? It works by mutual induction. I will explain something about induction to you soon. Mutual induction, that's how it works. So they can ask you that the operating system of a transformer is by what? It is by mutual induction. I will explain that to you soon. So there are two parts of transformer. We have a part that is called the primary and the secondary coil in a transformer. So a transformer looks like this. There's a metal plate. Now, this metal plate has around it a wound wire. Then here, then this is connected to an AC source. Then this is connected to external load. The one that is connected to the source is usually called your primary coil. Why the one connected to this is called your secondary. So looking at your transformer, how does it now work? Everything will still be based on what we have been doing all this while. So you should understand it as I'm about to explain it. The problem some of you might have is maybe you have not been trying. You have not been reading. But if you have been reading and it still looks difficult, please move on. Keep trying. Well, I not get like or not. We read over and over. We read and read and read. And we're always interested before we understood it. So, I already showed you what symbol of an AC is. So when you see a symbol like this, that's AC. So let's say a voltage has been generated now. So by a generator, that's your AC. It has generated a voltage. But you know how your AC works from what we just finished doing? Everybody look up. Do you know current can go like this? If it is an AC, current can go like this and current can go like this. That means there's a time. Let me just label it. This is A, B, C, D. You know, there's a time the current will go from A to B to C to D. From what we just finished doing. There's a time the current can also go from C to D to B to A. So meaning that the current will keep changing. So if it's an AC, there's current flow in this wire. Now, that current that is flowing in this wire first go like this. Then it will alternate again. Then the current will also go like this. That's why I said it's an AC generator. So if current keeps changing, one thing will happen. As the current is flowing here, you remember what we did here the last time? If current is flowing in this manner through this coil, we said something. We said we'll generate magnetism, Abi. And when I told you then, I said this is a solenoid, Abi. The magnetic field around the solenoid, I said it is just like that of a bar magnet. Now, because of the way the current is flowing, let me just put it this way, that it will go through the back, then up, 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 up. Because of that, we already know where our knot should be, right? So if I do like this, my knot is here. I'm just trying to recall some things. North, then south. At the end of the day, my field will go like this. Do you remember that? Now, let's now look at it. Let's now say this current that was going, this thing is now an AC instead of a DC. What do you think will happen to the current? It will first go like this, Abi, then it will flip again. Now, when it goes like this and it flips again, what do you think will happen to the poles of this magnet? That means as that current is going, that thing will keep changing too. I hope you're getting it. Now, if that means for this one to change, the field that first went like this, we also accommodate the turn, Abi, because by the time the current wants to start, the field will start again. By the time the current wants to go like this, the field will start again. So the field will first run like this. Then when you remove the current, when you know you are rotating the coil, and when you rotate the coil, we said something that there's a time that the coil will be flat. It will not be going through the field. Then when you rotate, it will go through the field. Abi, when you rotate again, it will be like this. So there's a stage. That's why that graph was looking like this. At a stage, the voltage will be high. At a stage, it will be zero. At that stage that is zero, it was like this. Then at that stage that is high, it was like this. All the flux was cutting through. So as you keep changing the flux, there to wole, the voltage will be a bit high. Then when it is all the flux, then the voltage will be at the maximum. Then when it's going back again, voltage will be zero. So that's why this graph keeps looking like only increase, only decrease, only increase. So same thing here. As the current is going through this wire, there is north and south. So this field, the current increase field here. And at the end of the day, when it's alternating again, field here to the zero, Abi, had to increase again. And by that sense, something will always happen here. Listen, no. As the current is flowing from here to here now, let's say it goes from here, then up, then go down. Abi, from what I've drawn, where should be my knot? At the B side. Do you agree? So I should have north here. Then I should have south here. Please, even if you don't understand what I'm saying, maybe you just join class. Shall listen. In Kotoma, be one more. When I keep talking, you will know it. Just listen. From what I've asked you now, all of you should be able to answer most of those questions that I've said. It's just that this knowledge is always climbing on top of each other. So, and even if you are doing it in secondary school, I'm not sure that we have to, even if you have some teachers, they might not have to explain how these things operate. They'll just tell you there's transformer. What's the function of a transformer? Increase voltage, decrease voltage. Oh, you know the formula. Vs over Ns is equal to Vp over Np. And you will cram it. And you go and be solving questions. But at a stage, you need to understand what is happening. And understanding what is happening at some points, little by little, will help you in exam too, to reason. So when they start asking you some questions, your brain will... Imagine they give you a question to solve. And you know, you now made a mistake in the question. If they ask me to get the voltage of this secondary now, and they said that the voltage of primary, my question, I already know my formula. Vp over Np equals Vs over Ns. At the end of the day, they said the voltage in primary is 100 volts. And they said I should calculate voltage in secondary. Now, I am getting 10 volts. Immediately I get 10 volts, I already know I've made a mistake. I already know I've made a mistake somewhere because the principle will not work that way. The way this transformer is designed, I should get a higher voltage here. So when I go to the option, I will look at, I might not even solve. I will just look for a value that is higher than 100 and pick it and move to the next question. Ibi tí yàtọ̀ ẹni tó wà intelligent àti ẹni tó kàn cram or who kàn gbọ́ stories ó dẹ̀ lọ tiẹ̀. Ibi tí yàtọ̀ wà nìyẹn. So you will get better, don't worry. So at the end of the day, what I have here now, from what I've said, as the current is flowing now, we have knots. By the time I have knots, then field will run. I don't want to roughen it. But this one is called soft iron core. Soft iron core in a transformer. You remember something when we started? I told you about magnetic field shielding. Ura, malo, so it's far. So it's far. The journey is far. I don't know, maybe my assumption, maybe we should just give basic definition. But assumption, maybe we should just give basic definition. But some of you, are you following the little things I'm saying? Or I should just give normal definition, give you formulas. Then we solve questions and move on. Because some understanding, they say I should explain this again. Ooh, online. Maybe once in class in that shape. I will explain this again. But explaining this is not my problem now because we have done it before. So, and we have rules that we used. But I'll come back to that. Now, what I'm saying here is that Faraday said something. He said, when there is a flux change, there will be an induced EMF, Abi. And we said that EMF will be directly proportional to the change in flux. So if you now want to generate EMF here, in quotation, to generate EMF, maybe, but we want to increase the value of the EMF. And you remember, to increase the value of the EMF, what will help me to increase it here? Number of turns, Abi, number of turns of the coil, then the flux that is changing. So in this place now, I have how many turns? Fewer turns, Abi. Iye ìgbà tí mo turn ẹ̀ ó kéré ń bì, but iye ìgbà tí mo turn ẹ̀ ó pọ̀ ń bì báyìí. So I've done something different. I made the number of turns here more. I made the number of turns here less. So by the time the flux from here is coming and is entering this place, is now entering more turns. So the EMF that is coming from here will now be increased because the number of turns here, imagine it is 1,000 turns. That means this EMF will become 1,000 times. At the end of the day, but if I did not put this soft iron, by the time this thing goes, it might not be everything that we enter. But that iron makes sure that everything is what? Entering here, so that you don't lose flux. At the end of the day, you're now going to have something generated here. So the voltage you generate here now, so is what will now be sent out, but a very high voltage. So this transformer now, this type of transformer will be the one that is from power station, because after generating the EMF, they increase the voltage and they sent it out. But the one in your home around here, the one that is coming from here is going to have lower turns, higher turns than the one around your home. So let me put it this way. Now, let me quickly explain this again for the person that asked the question. I will re-explain this perfectly. So, I don't know where to start from. But we said something in our previous classes. We said when you have a wire, a coil of wire, and I said something here that don't let us cram it. When you see question, you should just apply your rule to pick your answer. Let me just put it this way. This is a DC now. I'm not trying to make it an AC. We said something. There's current flowing in this guy. The current always go from positive to negative. That's why we depend on electricity. So the current will flow. As the current is going, it will come down, then it will come down, then it will come down, then it will go this way. That's the direction of the current. Now, as our current continues to move, you now want to determine the poles of this magnet. We used a rule. The rule is called right-hand grip rule. We used a rule then. We said if the currents are moving down, then you grip it like this. And where your thumb points, your hand like this, then your fingers will coil down like you are holding. Let's say this is the, guys, the currents are going down, so I will grab it like this in the direction of the current. In this place now, the currents are going up, so I will grab it like this. My fingers will go up, so this one will point this way. Shake. So pointing this way means anywhere this sound points is your knot. Anywhere it points is your knot. So as the current is moving down now, this is the knot, because if I grab it this way, this is where my thumb will point, and this is my south. And we always say that the field always runs from north to south, Abi. So the field runs from north to south. That's what we have said. Exactly. So that's how we got that. In this case, now that I know this is not, I just use my hand like this. Then the field will run. But I use AC here because that field will, oh mama, increase, had to decrease. Oh my, increase, had to decrease. So let's move on. So now we have two types of transformer. What's the purpose of transformer? Everybody. To step up or step down voltage. Now, the principles I explained here is just for you to understand how it works. It's not your problem. It's just that you need to have understanding, especially when you are being asked some questions. So they can ask you, on what principle does transformer works? It works on mutual induction. Is that taken? And now, what do I mean by mutual induction and self-induction? I will talk about that soon. But from what we have here, you can see this eléyìí kò ní battery, kò anything. The coil was just there, Abi. But because of the field that is running from here, low influence Ele. So Ele, this one, how many of you does not understand Yoruba? So sometimes I want to use Yoruba sometimes for everybody to get what I'm saying, but I'm going to switch. Ele, this one, what this one is doing, it's what is influencing this one. So it is mutual. Do you get that? It's not like whatever this one is doing is influencing this one. I'll talk about induction soon. That is why we call it mutual induction. Is that taken? So for simplicity. Now we have two types of transformer. We have what we call step-up transformer, and we have what we call step-down transformer. So by the time I start giving you questions now, I want you to be solving and be telling me why you have chosen your answer on analysis, not just picking answers. Show me why you have chosen your answer. So step down, the difference is this. If you want to step up, there's one important formula. E is equal to N the phi dt. But from the transformer design, we have made something important. The flux that is leaving this place is the same flux that is entering this place. So flux, this one is held constant. I hope you're getting it. In a field, the number of magnetic field lines that are coming out from here is what is entering here. Abi, at the end of the day, we have held that flux constant. So which means that in the primary coil and in the secondary coil is the same flux. But something is different. What is different in the primary and secondary here? The number of turns of those coils. So if you look at the formula, if I now say what can help me to increase the EMF, it is the number of turns. So the one with higher number of turns will be the one with the higher voltage, Abi, because E and N are related. So if N increases, E increases, voltage will increase. So in my step up, if you now look at the design, which one should be my step up? The one that the number of turns of secondary should be greater than the number of turns of primary, or the one that the number of turns of secondary should be less than the number of turns of primary. I want to step up the voltage. The primary source is where the voltage is coming from. So the secondary source is where the voltage is eventually either step up or step down. So now, if I want to step the voltage up, should my secondary turn be lesser than primary turn? No. Because the more the turns, the more the voltage. So my secondary turn should be more than the primary turn if I want to step up the voltage. But if I want to step down the voltage, my secondary turn should be lesser than the primary turn. But it's the same flux that will still enter because of the iron core. So now, for step-up transformer, your number of turns of secondary must be greater than your number of turns of primary. Are you there? For step down, your number of turns of secondary must be less than your number of turns of primary. We don't need to start drawing the diagrams again. So, if it is a step-up transformer, you can say that for this one now, E from the primary, let me put it this way. E from primary is going to be number of turns of primary, Abi, then change in flux of primary over change in time. While E secondary is also going to be number of turns of secondary, change in flux of secondary over change in time. But remember, the change in flux of primary over change in flux of change in time is the same thing as change in flux of secondary over change in time. Do you agree? The flux, the same flux, as the flux is leaving primary, is entering the secondary. So that remains the same. Meaning that from here, I can say from here now that my EP over NP is equal to minus the phi P over dt. Do you agree? From here to I can say my ES over NS is going to minus the phi S over the T. But the phi S and the phi P, they are equal. So I can equate this guy. So this guy and this guy are the same. Abi? So if this guy is equal to this, and this guy is also equal to this, then and this guy is equal to this, then I can say EP over NP is equal to ES over NS. So the only factor is just the number of turns. But for simplicity, in some textbooks, you can see this as VP over NP is equal to VS over NS. She get. That's the formula you need to know. So even if you don't have the knowledge of the stories I'm saying, forget about this. This is what you need to know. VP over NP is equal to VS over what? NS. So there are three questions they can ask you now. How do you step up a transformer? By increasing the how do you step up voltage? By increasing the number of turns of secondary. Abi, that's how you step it up. How do you step it down? By reducing the number of turns of secondary. Your primary is the source. So the secondary is the one that is increasing and decreasing for you. Do you get that? So at the end of the day, your transformer will do its job. Now, another thing you have to now note is what we call transformer efficiency. So efficiency is just talking about the rates at which one energy is being converted to another energy without energy loss. How you don't lose energy. If you can work effectively without losing energy. Are you through with the board? Oh, yeah, right. So I can quickly explain the efficiency. You can't see the board from there. You can copy here. Yes, Adeshewa. I change your sitting position. Ọmọ yìí tún dà. Ṣé Fatima ló sùn sẹ́yìn yẹn? Okay, Mary. Where is Fatima? Otisun. Is your name not Fatima? You are not sleeping. People should take your life serious. Can we move on? Can we move on? You people are always so scared. Bright, how far? Show okay. You know that if Bright falls once like this, it's like tsunami. Can I rub the board now? So, please, all these stories is for you that you want to really understand principles. And you probably have been learning for a while, and some things are getting better. It's for you. But if you are just a starter of physics, you don't need the stories. You just need your formula. And you need to know the difference between step up and step down. And you need to know, you don't even need to know all the stories I'm saying. Just know the difference between step up and step down and know this formula. That's all. They know this. They can ask you in JAMB. So now, efficiency of a transformer is just talking about the rate at which energy is being converted or power is being converted without loss of energy. I did not ask you to stand up. The rate at which power is being converted without loss of power. Without loss of power. So when you are able to reduce power loss to a very great extent, then you have what we call a great efficiency. All of you are preparing for JAMB now. Some of you are more efficient than the other. Your ability to do things and get good results is what we call efficiency. Someone can read for 4 or 5 months and not achieve something great, and someone can read in a month and achieve something great. It is still called efficiency. It depends on how you can reason, how you can join one or two together, how you can practically put your life to shape and make everything work for you. Why some people will see all of these things as challenges. Some people will find a way that, although I didn't really get much, I will find a way to understand it. And at the end of the day, you complain, and the person that decided to find a way will get better results, and you will still get very poor results. What we will see is your efficiency. How are you efficient in doing things, in managing your life? How are you efficient? So it's not about reading. Look at this now. Some people now will carry textbook that you have been reading, and you really do not understand. You carry a Bible, you read up to like 5-10 pages yourself. You read it. Bọ̀bọ́ yìí ò kí ń kàwé tó bá kàn ti ṣí báyìí, á kàn wò báyìí, aṣojú magnet lónìí. Bọ̀bọ́ yìí ò kí ń kàwé tó bá kàn ti ṣí báyìí, á kàn wò báyìí, aṣojú magnet lónìí. Ó dẹ̀ máa ní ó mọ iye ìgbà tí mo ti kà. Mo ti fi bí oṣù bí mélòó kan ka essential chemistry tí ò tiẹ̀ yé mi. Let me go and drop my work. Let me go and drop my work and go and face my academics. But after I've gathered enough money to pay for tutorial, then I now left to work. Then I went to face my academics. So it comes in different forms. Your ability to put in something and still get the best out is what we call efficiency. So if I ask some of you now to carry blocks from here to that side and the number of blocks, even for the fact that you have the same power, you might have the same strength, the same power, and one of you might just think about it. So I want to face this person. Why that one person is struggling carrying one block? How they be the same power? If both of you carry it, you might be able to carry just one block. But another person will take his time. He will not rush with you. He will just go and look for a longer stick. By the time he looks for a longer stick that is very strong, he will dip like 3 here, then enter the middle and put it. And he will walk and he will carry 6 at the same time. But you, 1, back. You come back again, 1. Now, by the time you go and come back, you already start crying. Why is life so difficult? You start complaining. But that one have taken time to look at it. How can I do this thing? I know Tiro. What they not Archimedes principle? Give me a lever and a pulley and a fulcrum, and I will move the world. You have, this is the word. What did Archimedes say? He's looking at it that, okay, if you want me to push this whole world, it might be difficult. But all I need is just a lever and just a fulcrum. It will be very easy. But it will be difficult to move. Efficiency. So apply brain. Be efficient. That same topic that you are finding difficult, I'm not saying that you should be parasitic. You should also contribute. That topic you are finding difficult, look for someone that understands it. Quickly explain to me in just, please, if it's 30 minutes of your time. There used to be some of my students then that used to complain that, and Dr. Peter, he will not teach me. I'll go and meet him. He will say he's busy. He's busy. Yes. You think I'm not busy too? If you come and, even people that want to pay me for private classes, I do not even have the time. You are not even paying me, you still want me to give you the time. I'm also busy. So just to see it that way. So all of you in this place are busy. Then one of them was not vexing that day that I will never talk to him again. I will never say anything to anything. You are just getting angry unnecessarily. Someone that you are supposed to roll on the floor and beg. Please, if it's 30, just look for 30 minutes. Help me to first think about you will teach me in 30 minutes and I will understand. When you have begged, I don't have time, I will buy you sweets. Please, I'll buy you sweets. I have a lot to read. I don't really have time. When you see the person tomorrow, have you eaten today? Will you like one Indomie? And after the Indomie, say, please teach me now. It's just 30 minutes. I don't have time. Next tomorrow, share you have pure water. Let me give you one pure water. He say, but I don't have time. I know what you are doing. But don't worry, we'll fix a time. But is this the way we were taught leadership and a lot of things when I was attending some conferences on leadership? There are a lot of things that we were taught. But if we put all those things to use, to me, it always looks like I'm using people. And that's why there are some things that I will never allow people to do for me. I like doing my things myself. So that it does not look to me as if I'm using you. It does not. Even if you want to force yourself, you can ask those ones I used to stay in hostel. If you want to force yourself, you can ask those ones I used to stay in hostel with those days. As old as I am, I will go downstairs, go and fetch my water, so that you don't start feeling like, oh yeah, Miriam, which is part of being, and sometimes it's better. They can say that you can use money to buy time. You can use money to buy time. When you have money, you can buy time. It's better you go hungry and say, some of you, stinginess is not luman paying. You have 500 naira and you have a lot to learn. I can't say, I want to buy 1 hour of your time. I will buy you fan yoga. That fan yoga might save you 1 week of stress. And you buy the person fine yogo, jọ call me ní thermochemistry, kò yé mi rárá, jọ call me. Bóun dẹ̀ ṣe mu fine yogo, á dẹ̀ máa kọ́ ẹ, inú tiẹ̀ náà máa dùn. And at the end of the day, it is win-win on both sides. But o máa fẹ́ kó kọ́ ẹ ò tiẹ̀ lè ṣe kọ́kọ́ fún. And at the end of the person too will be gaining. So that's why when you teach too, you will gain. But however it is, that kind of logic to me looks more like, it sounds more like you are using people. However, but if you positively think about it, you can't do everything in life on your own. You can't. So there are a lot of times you have to learn from people, one way or the other. So now, transformer. You remember from, please listen, no. You remember from electricity that power is equal to IV. Abi? Power is equal to IV. So there is a current that is flowing in the primary, Abi, and there's a voltage that is generated in the primary. So the power transmitted from the primary is going to be IP, VP. The power in secondary is going to be what? IS, VS. I hope you are following. Now, if this power from primary equals the power that is coming out in secondary, then you will say it is efficient. So a transformer is said to be 100% efficient if there is no power loss. A transformer is said to be what? 100% efficient if there is no power loss. Meaning that power input is going to be equal to what? Power output. Emmanuel Mori, Abajo Terra wine, you want to buy my time? Wisdom. I'll drink the wine now so I will have more energy. Power output is equal to what? Power input. What's power input? IP, VP is equal to IS, VS. So as much as possible, you all need one another. Just be good. Just be kind. Be kind. Be kind. Be good to people. Suffer small. Some of you are too selfish. You like yourself too much. I'm not saying that the person that is not teaching you is selfish. Oh. Everybody has reason for that. But you that they said that they don't have time to teach you, you should understand that you are all busy. It does not mean that and you don't know what the person has been going through. You don't know how long that person has even faced his own struggle. And this person does not want to teach me. This person, some people are naturally selfish. That one is different. Some people are just selfish. But please, you all need one another. Be kind. Be nice. Don't be rigid. And avoid bad-mouthing people. Avoid, especially girls. Boys, they know how they do it too. Avoid bad-mouthing people. Look for people's progress. You have to learn all of these things. I don't know who was, I think one of primary students yesterday messaged me, Farouk or something. He was like, he wants to even know what's the purpose. I think he's in university already. He was asking that what's the purpose of first class? That all these first class that will shout. Why is it that someone must have first class? He said, what's the purpose of first class and something in certificate? So I told him that first class opens opportunity for you. First class is what we open doors, opportunities, things you never even thought of. First class will open the door. First class will give you position. When they want to employ people now, they will look at all the certificates first. oh, we want people that are first class. The all of you that are 2-1, 2-2, third class, only mark on third class. Even some courses in university at master's level, you can't do it if you did not graduate with 2-1 or first class. If you graduate with 2-2, you will still go back to school to do a professional course before you can now do masters in some schools. So first class is that top that just make you unique, that everybody will see you, and companies will come and say, oh, NNPC, they want to employ you. MTN, they want to employ you. And this Mobile, they want to employ you. Chevron, they want to employ you. Different companies will come. I don't know if that still happens today. But on your convocation, another thing is first class. Your parents will be seated among several other parents, and they will start calling your names several times, and they will tell you to come forward, and they will keep awarding you, and your parents will be blushing, and they'll be awarding you, your parents will be blushing. So first class can give your parents joy. So at the end of the day, you also step forward, and they say your parents will also step forward, and they will also stand up, and they will come and take picture with you in the presence of ọ̀pọ̀lọpọ̀ parents. Our parents are akuku ti bí náà. Ọlọ́run máa bá wa ṣàánú ẹ̀. So, but first class does not now equate to success in life. It does not equate to success in life, but it's a potential thing for you to be successful in life. But one of the things that cannot be the problem is, I now told him, I said, it is not first class that means success in life. First class will get you position, but your character will keep you in that position. Your character will start bringing promotion one way or the other. After they pick several first class, they will still do tests. They will do oral interview. They will do a lot of things. But you are a first class graduate. One first oral interview for you did not even build your mentality. So you have to balance everything. So have good character. Ẹ fi ìwà rere kún ìgbàgbọ́ yín, àbí? So IPVP equals what? ISVS. Which means that now look at this guy and this what I'm about to do. You now have VP over IS is equal to VS over IP. Look at the difference also, don't make that mistake. If you want to even make mistake, just write power output equals power input so that you do it yourself. Always do it this way. People used to make this mistake. You can see that what I have here is VP over IS. So it's never VP over IP, but here it was VP over NP. Do you get that? So don't make that mistake, please. So what does VP represent? The voltage of primary, Abi, and VS represent voltage of secondary. Currents in secondary, currents in primary. Now, if you now notice something here, VP is inversely related to IP. And that's where there is a bit of confusion. In power transmission, when you are treating electricity, if you increase voltage, you are reducing currents. So we will now talk about factors that affect the efficiency of a transformer. So there is no transformer that is 100% efficient. There will always be power loss. And now is power loss. Power is lost by P is equal to I square R. That's why I'm saying that electricity is very important. Now, P is equal to I square R. R is the resistance of the wire that the current is flowing through. I is the current and P is the power. So if I want to get power loss now, I can calculate it using this formula. Now, I want to send voltage from power station to town. If I want to reduce power loss, then I have to reduce the current. If I send it at high current, there will be great loss in power. All these things. Well, to the level only we score 100 in physics, so you will score 100. It's not prayer now. You will score 100 in physics because There are some questions that they will give you. It requires understanding. If you don't understand it, you might just be applying and you will see the option there. And you will come out and you feel like, oh, I've done everything right. And you still see like 60 over 100. You still like 50 over 100. You be like, but ṣebí P is equal to IV ni mo dey solve na mo rí voltage, mo rí current, mo dey get power. Ó dẹ̀ wà l'option. Whereas you really lack understanding. And lacking understanding cannot make you get 100 or 90 something. So please, as much as you are reading, work on your understanding. It's easier this way, especially in this generation. So that's why some of you feel like I read, and things are not coming out well for me. You lack understanding. Please, work on that, and you can pray for it. So, now, from what you have here, from this scenario, if I have a high voltage, then it has to come with a low current. Now, why am I saying that? We are going to see soon. So, note something, that there is no transformer that is what? 100% efficient. So, if they now say calculate the efficiency of a transformer, efficiency of a transformer is given as power output, Abby, power output over power input times 100. Which one is usually your power output? Secondary. So, my dear. That's ISVS over what? IPVP times what? 100. Do you get that point? So you are putting in power at primary, then you are getting it out at secondary. So that's what we call efficiency of a transformer. So can we move on? Ejo, with the mode of this period, teachers here to share topics. Don't kaluku focus later that. I see no reason why you can't score your 100. Because normally, if there is no time, all these things, Simon waste time, Simon farabale, explain for in formula, we'll move on. So, if you see questions on magnetism and you still miss it, you probably did not do your own assignment. So, why is it that transformer is not now 100% efficient? So why not 100% efficient? Why is transformer not 100% efficient? So there are some things that happen in a transformer. Number one is resistance of the coil. Number one is resistance of the coil. You know, the coil is like a wire, Abby. And when you have coil, for voltage, you remember, voltage is going to be equal to IR, Abby. So if there is resistance, that can affect current, can affect voltage, all of those things in electricity. Or you also remember that R is equal to rho L over A, Abby. The higher the length of the coil, the higher the what? The resistance. All these things are from electricity experience. R is equal to rho L over A. If the length of the coil, and you remember we also said you are going to get a higher voltage if the number of turns of coil increase. But see why I told you number 2 resistance mama 2 mashele, and all of those things we have effects. So the higher the length, the higher the resistance. So for the coil, and that will make energy to be lost, because if resistance is high, then power will be lost, Abby, as I square R. Power will be lost. Another thing is what we call eddy currents. Eddy current is another thing. So note something, they can ask you, let me put it here, corrections. So in order to correct this error, what do? We need to use coil of large cross-sectional area. So let me explain that. Resistance is equal to what? Rho L over A, Abby. If the wire is very long, then the resistance will be high. But if the wire has a great area, resistance will be low. So which means for you to counterbalance the effect of length, you can increase the area. Do you get that? If you increase area, resistance will be low. If you increase length, resistance will be high. So in order to counterbalance what length will do, you have to increase the area. What I'm just saying here, you will learn it under current electricity. Under current electricity. Now, eddy currents. Let me just explain that in a simple manner here. I can rub this guy now. Don't worry, we'll solve questions on everything. If you had wanted me to teach this thing in 1 hour, I would have taught it. So it's not, but there is no reason. I have several reasons to rush, actually. Shonpele, timekeeper. What's the time? We share one. Is that not blessed? We're on continue for year. Very soon. Ejeba mi woja àti ro. Abo kin bi epon. 12:59. I know majority of you people went for VG, abi. Epele. Shewa. Blessed. So please don't sleep. Don't sleep. I know you went for video. So let me just explain it this way. If you have a metal plate and the metal plate keeps changing, like keeps moving in a flux. Let's say you have a magnetic flux. Then you have a metal plate. And the flux keep cutting through the metal plates. Then inside this metal, there will be a current generated. The current will go in a circular pattern like this. Currents will go in a circular pattern when field is passing through the metal plate. That current that is going in that circular pattern in that metal plate that is cutting through the field, we call that current eddy current. So you remember in a transformer, we also have a metal plate where we wrap the coil, abi? So as the field keeps changing, such current can be generated in this metal plate. And that current that is generated in the metal plates can affect this guy. It will start making the metal to get very, very hot. Heat. And the heat can have negative effects on the transformer. And at the end of the day, we call that current. We don't need it. What is it doing there? So we call it unwanted induced current. So let's write on eddy current. So eddy current is an unwanted induced current. An unwanted induced current generated. An unwanted induced current generated as a circular pattern of wave, something that looks like wavy, as a circular pattern, generated as a circular pattern in a metal plate. In a metal plate, moving through a magnetic field. Unwanted induced currents generated in a metal plate, generated as a circular pattern in a metal plate, moving through a magnetic field. And you know what induced currents always do from what we did on Lenz's law? What's the purpose of induced current? What does Lenz's law state? The direction of the induced current always acts to oppose the motion, Abi, producing it. That's Lenz's law. So the induced current here too is trying to stop the flux that is generating whatever it is. So it's trying to stop all of those things, and that would be affecting the efficiency of the transformer. So if they now ask you, how do you reduce eddy current? So right, eddy current can lead to great heat. Eddy current can lead to great heat or energy loss in a transformer. Great heat or energy loss in a transformer. So how do you get rid of eddy current? So in order to correct that, eddy current can be corrected, eddy current can be prevented by using a laminated soft iron. By using a laminated soft iron. Just like you are insulating it, a laminated soft iron. So you laminate it to like insulate it from conducting so that can conduct. Is that taken? Another one is called magnetic flux leakage. That can also affect the efficiency of a transformer. You remember when I told you the other time, I said all the flux coming out from here should be entering the next one, Abi, through the metal. But what if it's not everything that is entering? There are some parts will not enter. She gets. So something like that is simply what we just call the leakage. So, and in order to prevent that, to prevent magnetic flux leakage, we use a soft iron core. That's why we are using this iron, so that it can concentrate the magnetic field. So we are using the soft iron. So the last one is what we call hysteresis loss. Hysteresis loss. Hysteresis loss. Hysteresis loss is just talking about the energy loss due to, right? This is the energy loss in a transformer. Energy loss in a transformer due to continuous changing magnetic field or flux. Due to continuous flipping or change in magnetic flux. Now, this one is just like this. And you know, the current will keep changing. The current will go like this, also come like this. So there is a time that when the current is going like this, field will go like this. When the current is going like this, the field will go like this. And that keeps happening every time. And you know, even if you keep doing things back to back, there will be something that will be wasting, like energy change, heat change. It will be generated in that transformer because that flux just keep changing, alternating. And at the end of the day, by alternation, it will start making that transformer to get hot. Just like overworking. She gets. So it's like overworking the machine. And that's one of the things about hysteresis law. But all of those are just by the way. The one majorly they ask you in JAMB is eddy current. So get used to eddy current. Is that taken? I like to even read new school physics on some things. So That's all about transformer. Abikilo kura. So let's talk about induction. Induction that I used to explain transformer. We should have done it before transformer, but let me just quickly brief you. Induction. Induction. When you get to AC circuit, to be hearing induction, blah, 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 blah. So what is induction? So inductance, like resistance. The symbol for inductance is L. Inductance. This is an opposition. Inductance is an opposition created in a coil of wire. As a result of currents. Have you done it? As a result of currents flowing in the wire, that is generating a magnetic field. Is the opposition produced in a wire as a result of current flowing in a wire that is generating, is that how I put it? That is generating a magnetic field. Full stop. This magnetic field change induces a current in an opposite direction to the current producing it. This magnetic change, like flux change, this magnetic change induces a current in the wire. That opposes the current producing it. Induces a current in the wire that opposes the current producing it. Full stop. So what am I saying here? Is the same thing we have been doing, but just for basic. You know the function of a resistor in a DC circuit. Your resistor helps you to oppose current, Abi. You also have something called an inductor. So let's just say, let me just use a DC, for example. The symbol for an inductor is usually like this. Just for understanding, this is an inductor. Current will start flowing in this inductor. And as the current starts flowing, remember, if there is no current, there will be no magnetic field in this coil of wire, Abi. But by the time current starts flowing, the current will be flowing at different rates. And when current starts flowing at different rates, eventually magnetism will be generated. But if the current is high that is flowing, the magnetic field might be high. If the current is low, the magnetic field might be low. And as a result, when you start changing magnetic field with time, like own increase, own decrease, what will happen? There will be an induced current. Just like what we have been doing. Here now, there is a battery that is allowing current to flow. But as the current is flowing, it's changing field. And as the field is changing, what do you think will happen in the wire? There will be an induced current. There's a magnet now. In this case now, there is no battery. But because I'm moving magnets now, I'm moving these magnets into this coil. That's where we started. As I'm moving this magnet into the coil, what will happen to the coil? There will be current generated. Abi? I hope you're getting it. How did current get generated here? Because there's a magnetic field entering the coil. Is that not where we started from? From Faraday's law. Don't look like you are going to die or getting the field. That field is now, the field is increasing, is decreasing, is increasing, is decreasing. As the field is increasing, there's a change in flux. And that's Faraday. There's a change in flux. And as there's a change in flux, that will be associated with EMF, Abi, and that means that current will start flowing in opposite direction to this current. What generated this field? This current, Abi. You are the one that used to move here. If you are the one moving the magnet, that's when there will be current. But now you are not doing anything. You only connected the wire. Then when you connected the wire, you connected it to a battery. Then current start flowing in that wire. You are not moving magnets. But because this current is flowing, magnetic field started being generated. And by the time you generate magnetic field, what did Faraday say? As the field keeps changing, this place will generate current. Forget this current now. What did this current do? It generated the field. What's now the field doing? It's generating another current. But the current is generating in this field. We oppose this one. Because the current being generated as a result of this field wants to stop what is generating that current, that field. So in this sense now, we say that the current, this is the current that is coming from the source. This is the magnetic field that is generated as a result of this current. But this magnetic field, because it's increasing, is decreasing, it will also generate an opposing current that will come in opposite direction. That opposing current is the induced current. Now, this knowledge might not be open to everybody. Don't be sad. Are you sad? Yes, yes, you are sad, I know. Smile, smile. Be happy. It's not every knowledge. Sometimes when I'm teaching you, I try to bring myself to your level at times. Because sometimes, even before we understood some things, we did a lot of reading, a lot of research, a lot of work, and all of those things. So I always consider you that, how will you understand this thing? Because most of the things we are talking about looks imaginary. It looks imaginary. But if you understand from the basics as we have been coming, you would have known that you would have gotten what I'm saying here. Now, listen. In this place now, I've combined two things. I used electricity to generate magnetic field, which was where we started magnetism from. That when current is passing, there will be what? Magnetic field generated. Then we now move to the second chapter of magnetism, where we said if you move a magnet, you can generate current. And that current is being generated as a result of change in flux, according to Faraday. And that current being generated is called an induced current. And the induced current you generate always acts to oppose whatever is generating it. What is generating this current here now is this field. What generates this field is this current. So there are like two things we have combined. We have used electrical energy to generate magnetic field. Now we are using magnetic field to generate another electrical. But this current being generated now always acts according to Lenz's law. We did it in experiments. Always act to oppose this one. So meaning that if the voltage I am moving with is the source voltage, then the voltage induced by this inductor is usually called the back EMF. This is the EMF of the source. There is back EMF. That will reduce the EMF of the source. So if the EMF of the source is supposed to be 12 volts and there's back EMF of 2 volts, that means what is working in this circuit is just 10 volts. Do you get the point? No, I know. You have not done current electricity. What's EMF? If you are asked to explain what EMF is, can you explain it? It is the work done in moving a unit charge round a complete circuit, abi, it's just like the voltage of your battery, the EMF of a battery, what will help you to do the work in driving the current. So when you do current electricity to that level, you will understand what EMF is. And we always have that EMF is equal to external voltage plus internal voltage. Abi, external voltage is I sub R, IR. Internal voltage is I sub R. Now, this one is only related to the battery itself, in case I'm talking about resistance. Because what you do at DC level is that you are only going to connect to a resistor. You usually connect to a resistor, not an inductor. But when you get to AC circuit, you will now be connecting inductor, resistor. That's when you will now be saying calculate the capacitive inductive reactance, calculate the resistance, calculate capacitive reactance. Because all of these guys, they are serving like resistor. They are opposing what is produced. If I put a resistor here now, at the end of the day, my battery, the job my battery will do, the resistor will be opposing that job. Abi, it does not want current to flow easily. And if it's not wanting current to flow easily, it's opposing that current. So, what I've said so far, just hear it. Just hear it. Some of you, the problem you have is that you know, sometimes go and ask some of you that probably repeated JAMB class. Go and ask them that what is the feel now and what was the feel then. Ask them. I'm just saying something that's, ask them that when they were around then, did they study? When they are around now, what's the difference? You know what I'm saying? At a time, some of them came and they wanted probably medicine as the most competitive course. And they know they have to score above 300 and something. And they read, they did everything. And when results came, they saw 250, 240, 220 something. And they felt like, what else do these people want me to do? I've read. Mo kàwé, mommy mi gan máa ń bẹ̀ mí kí n lọ sùn ni. I have a girl that when she just came, she wanted nursing that time. When she just came, she read. Her mom will even come to primers. Yinka, bá mi pọ̀ ọmọ yìí, ó fẹ́ parẹ́ sí mi lọ́rùn ni, inú ẹ̀fọ́ ló ń sùn. The mom will say that she should go inside to go and read, but she will say no, she wants to sleep in mosquito so that she will not be able to sleep, so that she can read all night. She read all her eyes out, and I knew she was reading everything. But eventually, she had, although she has written JAMB before she came to Primax, when her mom brought her then, they said it's A level they want her to now do, not JAMB, because she said that she's never writing JAMB again. She's tired, she's this, she's that. And I told her, I said, you going for A level now is just like changing your battlefield. There's a battle that you already know, that you are facing. All you just need to do is win in that battle. But there's another battle you just want to go and face. And facing that new battle, you will have to learn new strategies. And it might be a problem. This is your first time in Primax, so calm down. You will pass JAMB. You want to study nursing, you will pass. I told her. And I did all the convincing. I talked to the parents, I talked to her. And she started reading. She used to sit at the front too then. And she formed a colleague, Isoyin Consola, Oyin, Feyi, Tomi, and Juliet, and Miriam. Miriam, your elder sister. So Miriam is studying medicine now. Miriam too had nursing. The 5 of them had nursing. Out of like 500 and something that UI will pick that year, the 5 of them topped the lists. One to tell around. We were doing class. After class, the 5 of them will go to the back of the class. They'll go and be solving questions, be reading. And one to tell around, it was Miriam. Yes, it was Tomi that topped the list. Tomi too, that was her first JAMB. She had the highest. You would have seen their video. I did a video for them on YouTube too. She had the highest. Then followed by, I think, Miriam. Then followed by Feyi. then followed by Juliet, followed by Oyin, then followed by Juliet. But Miriam still did not accept the nursing. She said it's medicine she wants, and she wants it in OAU, and she had to write JAMB again. And the other 4 accepted the nursing day they went. She wrote JAMB again, and she still now passed, and she passed her post-UTME. She studied medicine in OAU. She's in 300 level medicine. The other 4 are in 400 level nursing. So a year difference, because she had to wait again. So what am I bringing out? When Oyin did everything, I want to say that upon all the reading, upon all the fights, upon all the struggle, this girl still scored 276 or so. Imagine it had been medicine she wanted that year. Upon all the convincing that and she read, and she's still sound, she will be at the front, she will still ask questions. Don't even joke in her presence. The way I used to talk here, Oyin would have said, let's continue. She wants to just quickly learn, cover. She was ready, fighting, and all of those things. But at the end of the day, she had 270 something. And what's now the point? When that 270 something, I think after writing UI post UTME, I registered them for JAMB again, because then I don't take risks. I used to follow them. So I registered all of them for JAMB. My sister too, Feyi too had Feyi had 280 something. Tomi had 276. Then Miriam had 290 something. She even brought that one. So at the end of the day, I think Juliet too was 280 something. Juliet was 280 something. So look at the way they read with the intensity. When Feyi came with 220 something to primates, and she said she was going to study microbiology, medical rehab also. But OAU gave her microbiology, so she did not accept it. So she had to write JAMB again. That one is my cousin. So now, from the whole story, they did what reading is all about. They read. But at the end of the day, when UI started processing admission for them, they've not seen admission. But then, JAMB too close. I always advise everybody, shall register for JAMB again. Because I've had a student that was waiting on admission before. He should have graduated in OAU now. He was waiting on admission, and they were promising him that one too. Your whole level is not complete, and you are saying you are waiting on admission. How? And this person is promising you that you will do the admission, you should not worry. And you can pay the person. So, JAMB fee close. He did not register for JAMB. The next year, when he will register, he had to register for WAEC, and he had to wait 3 years after. Go to Padahari microbiology. So, I don't take that risk. So even if, except I know you have met the cutoff, but if you are the type that someone is promising admission somewhere, and you are sitting on that, and you are not trying to make a move, at least if that one works, Sefini, you can go. But if it does not work, you don't let JAMB close and say, they have promised me, oh my work, oh my work, oh my work. So what I want to bring out is these people no longer read as they used to, but they were still just around once in a while, and they wrote JAMB again. The ones that wrote JAMB again among them, all of them, they scored above 300. They scored above 300. And what now makes the difference? Is it because they did not read the first time, or because they did not read the second time? Experience. Their intensity that first time really helped them. So it's just like they've built foundation. So now hearing it the second time makes it so clear that the moment you say something, but someone that is hearing it for the first time, I used to tell you something that if I meet you today and you tell me your name, I might forget it tomorrow. But by the time I see you tomorrow and I ask you again, what is your name? And you tell me again, I might still forget it. Sometimes, the only way I do not forget name is that I will attach you to something. Is either I attach you to someone that I know before, or I just try to call your name over and over. It's the same thing with academics. That one is just a single name. Oh, there's often now imagine all the information I passed today. Ola. But by the time you start, you will see, the more you get used to someone, the more, even before you know it, you have mentioned that person's name. But by the time you look at all of these things, you are not practicing, you are not going over it over and over and over, you are not trying your best to get from people. Hard to know, ask questions, do your best at the end of the day. So first time I'm saying these things, they might look magical. And the major reason they look magical is that if you tell me an Igbo name and you tell me a Yoruba name, which one do you think I'll register the most? Why did I register Yoruba? Because I've seen a lot of people that bear that same name all around, over and over. Abi? But the Igbo name will look like, I will even ask the person. And if you go to Igbo land and you mention one Yoruba name, that Igbo name is what they will register easily, no matter how long or how corny the sound might be. I hope you're getting my point, because they are used to it. So I might be saying that, how do you people always keep Ibenware Chukwu? How did you keep that in your head? Whereas some will be like Ogumurede, and you will remember that one. So it is what it is. This thing might look complicated for the first time. They might sound difficult for the first time. But your consistency, your hard work, your readiness. Many of you know example. I used to use this guy as an example a lot. This guy is studying nursing in Unioshu. What's her name again? Bola Amidat. Bola Gade. Her sister was one of the people I knew in OAU too before she came to Primax. And you know, that mindset, she wanted nursing. And anytime I pass in that hostel, this girl is always reading 247. Amidat is always reading. But whenever we write mock, Amidat will not do well. And at a stage, she felt like, hey, a lot of people have known me in this hostel to be the one that read the most. And if I write JAMB, I do not do well. They say, Hashebo Lomanka will do. And she cried that day. She was crying literally. And she came to meet me. And when she was crying, to talk to me that, sodium, this and that, this and that. And I told her, I said, the fact is that I sincerely told her, I said, the fact is, your background might be poor. You might not have that result you are looking for. Don't put it on people's expectation. Don't, because your friend have seen it, you now said, oh, you want to put it on people's expectation, you are reading. Then, in yellow one thing, instead of you to continue. I said, what you are just going to do is continue reading. Just don't stop. Just continue what you are doing. Don't bother about what anybody is saying around you. Let them say, I will look away you. Just continue. And at the end of the day, when the JAMB result came out, I think she had 223 or so. She had 223. All I just did was to encourage her. Even though her parents already, her sister was like, she kiniko. I encouraged her. She went home. She came back. And when she came back, she now wrote JAMB again. She now had 325. If she had given up that first time, I feel like, I cannot know book. I do not know this. At the end of the day, she will never even know her true potential. She will never discover her true potential. But that time she scored 325 is not when she started the work. She had been working. The work that got her 223 was the one that gave her 325. You people might not just know. The time she now wants to study again, she now started picking those things again, started going through it again. She now started saying that, so nǹkan tí mi mọ̀ ń gbà ẹ́ lélẹ̀, nǹkan tí mi mọ̀ ń gbà ẹ́ lélẹ̀, àṣẹ wa máa lajú, á máa rí. So this was what I really did not know then. This was what I really did not know then. It's the same thing everywhere. So please, if you are hearing some of these things for the first time, it might look strange. Don't be scared. It does not mean you will see it in the exam. You might not even see it. It might not come out in your own question. Don't say amen, go and prepare. It might not come out in you don't know where your questions will come from. So that's why you should just be open-minded. You will see some people, they will write the JAMB once and they will escape. Because questions will come in their favor. So you should pray. àwọn máa kọ́lẹ̀ kan kò mí pé o máa kàwé náà o dẹ̀ ní wàá pass. I have a girl then that Tosin, she's in Lautech studying medicine. I remember that year when her mom came to Primax. They wanted to see CEO, they wanted to see Primax. I was wearing slippers. I came out. The mommy just looked at me like this. The very first time. I was like, they told me about Primax. I'm coming from UCH. A doctor recommended Primax, this and that. Where is the CEO? He's not around, man. So at the end of the day, I told her that I'm the owner. She now looked at me. She said, she thought that the way they described Primax and talked about me and everything, that she thought that she called me, she would see a man with a big belly, all of those things. I said, Emma, worry. It's not about the belly, it's about the brain. So at the end of the day, when this girl started her class, the same way people have been calling me, then we went to use a Reliance, one place down there. The same way people have been coming, people will come and they will talk to them. I wrote JAMB 8 times. I wrote JAMB 7 times. Immediately thinking about it, I wrote JAMB 7 times. This girl will start crying. She will start crying. And when she got home, she told her mom that, hey, people that got all these courses, they faced a lot. She cannot do it, but she wanted medicine, this and that. Her mom called me that every time she gets home, she's always crying instead of reading. I now called her, I talked to her. I said, the fact that someone did it 3 times, 4 times, 5 times does not mean you have to do it. You don't know different person's background. You don't know the journey behind everything. Someone might come. Look at what Jide said now. If Jide told you that I wrote JAMB 5 times, or I've been in primary since 2021, and I gained admission 2025 or so, many of you will be like, 4 years. But now, when he was telling you the secrets behind what led to most of those failures, Abi, he was telling you everything. He was now warning you to be careful. Don't be like me. So you might be in primers, instead of putting up the effort, there are a lot of errors you two might be doing. Instead of putting up the effort, instead of not crying, you are crying. Instead of trying your best to cope, is it not the same boy, what's his name, that is in dentistry, that came recently to talk to you people? Gideon. When did Gideon join Primax? January. What did he score in JAMB? Above 300. Last year, he joined Primax January last year, and he scored above 300. So it does not matter. And what did he do? Is it because he was brilliant? Imagine that immediately he now came to Primax in that January. One girl is now crushing on him. Into his crushing on the girl. And at the end of the day, they did not read. Both of them start talking. And at the end of the day, throughout the whole months, tó bá ti fẹ́ gbé ìwé díẹ̀ báyìí, a tún rí angel lẹ́gbẹ̀ẹ́ kan. And he can't really control it. And he had issue. He will now have to wait another year. But over there, I wrote JAMB last year, I did not make it. He will not tell you that I have a crush last year. I did not make it. What were JP's experience, aside family challenges, Abi, that he faced? It's not everybody that can survive some things. Your dad is the only one doing all the running around, trying his best, and suddenly at a point you want to write an exam that he has paid for you, that is carrying all the load, he died. And he wants something for you. If there had been no support, maybe, we don't know what could have happened. But he sure kept on pushing. There are some things I just told him that everything in life comes with stages. So his own. Now, aside that, aside the family challenges, he's still not carrying other people's load again. Every time. And indirectly, all the load was still weighing him down. So, you all have your reasons. Just know what you are doing. Some other persons that came to Primax, what affected them was their background. Some people cannot even speak proper English. They cannot even get what you are saying. That's what delayed them. So they took their time to learn understand English, understand academics, build their lives, and they got the progress. So you can't compare one another. Don't. Because the person next to you is doing well and you are not really doing well, you don't compare yourself. Just try. Keep trying your best. Everything will work out for you at the right time. And God has a plan for you. So don't be scared. I don't understand. Okay, thank you, sir, for the lecture. But, sir, what makes a transformer to blow? What makes a transformer to blow and what causes it to blow? What cannot blow? Does your charger not blow? There can be surge. There can be, please, there are some questions. You know, I told you that there are some questions that you should be asking an electrician or you should be asking a doctor. You cannot tell me that why did one person's leg remove? Like, there are several reasons for legs to remove. Why are you asking me? Yes, now. Yes, that's what we call surge in electricity. Have you not seen that sometimes you have high voltage at home? Your bulb will just, then it will go and the bulb will blow. Eh? Yes. That one has been stepped up. That one cannot enter your house. So. No, now they would have designed the transformer. It's just the surging flow that can, and all this lightning you are seeing, it's not like there are no sparks. There are enough charges in the air. But sudden discharge is what. Why is it that you just feel sudden electric shock? There are electric currents, there are electrons everywhere. But maybe due to rubbing, due to some things that have happened, then you touch. If wire breach too, things can happen. Wire can breach. A lot of things have been happening to me too now. All my charger have been pull. So I don't know what's causing it. An electrician that I called too is asking that, kí ló lè fà náà? Ó possible kò jẹ̀bi, ó possible kò ní. So please, now you see what happened here. Because of this thing that is happening in a single wire and the wire influencing itself, we call it self-inductance. So you can see, like the other one I did for transformer, if it is now, look at this one now. For this other one that I did for transformer, in this place, there's just a single coil. Here now, there's a coil. So what is happening in this coil is affecting what is here. At the end, there's a field flowing through this one too, Abi. And as a result of that field, there will be current flowing too. But what brought about this field is this one. What brought about this field for this one is the same guy. So if it happens in the same coil, we call it self-induction. If it happens as a result of another coil, we call it mutual inductance. So, but let's move on first before we talk about the types. So, from what I've said here, I said there is a current flowing and the current generates magnetic field. I already gave you the definition. If you follow the definition, the current generates magnetic field. The magnetic field generated what? An induced current. And that induced current always acts to oppose the motion producing it. So we now have this formula that the EMF So the purpose of the talk is just to encourage you not to give up. So, and that's what helps you. We have types. So we have self-inductance. So when it involves a single coil, and that single coil generates a field, which generates an induced current that is opposing the motion of what is producing it. Then we have mutual. So mutual inductance is when one influences the other. Then we call it mutual inductance. So when what one does affects the other, we call it mutual inductance. So we can combine inductors just like the same way we have it for resistors. You can combine inductors in series. So if you combine inductors in series, this can be your L1, this can be your L2. When you combine resistors in series, what do? Do you add or you do the inverse? You add. It's the same thing for inductor. So when you combine inductors in series, you will just add. So that's going to be total inductance A. I was testing you. So L total is going to be L1 plus L2. Sorry. So for parallel, so when you combine inductors in parallel, this is L1, L2. So that means 1 over L total is going to be 1 over L1 plus 1 over L2. Then finally, energy stored in an inductor. Then I'll give you short notes on. So the energy stored in an inductor or the work done is given as half Li squared. So if you double the currents, the energy stored in the inductor will quadruple. Is that not blossom? So if you double the currents, that will be 2 squared. That's 4, Abby. So that means the energy will quadruple. So that's the energy stored in an inductor. Please help me to keep the notes very well, so I can. Well done, sir. Samuel, I'm a conductor. Kiloku. So now, the next one is the carbon microphone. The carbon microphone is a device. The carbon microphone. Have you written what's on the board? No. Happy Valentine. Then,
Used to bust like huh? We should be showing the fan. You are the she was the fan. Sleep again. I'll bring the camera. What's the check? You. Your cheap data.
is used to transmit sound signal into electrical signal. Is used to transmit sound signal into electrical signal. As a result of varying resistance, is used to transmit sound signal into electrical signal as a result of varying resistance of the carbon granules, varying resistance of the carbon granules, carbon granules like black carbon, of the carbon granules that are set in motion Induction coil is a device used to So to what? I said induction coil is used to what? Step up the voltage of a DC. While transformer is used to step up or step down the voltage of an AC. So a capacitor is used to prevent electric spark. A capacitor is used to prevent electric spark in an induction coil. A capacitor is used to prevent electric spark in an induction coil. So far so good. Let's all. Okay, so far so good. Let me see you. You call it shade blue. Why is so loud? About your two red and white. So this to a great extent, we have done magnetism. To a great extent, we have done magnetism. There are just one or two things I need to talk about, guys. Like magnetic domain. I think I did explain that. But so far so good. We have done we have done a lot on magnetism. So everybody bring out your past questions. And let's solve questions. Oh yeah, your past questions. So what's the time? When is 2:30? So if you have questions on magnetism, let me see. Or bring out your past questions so I can give you questions at least on what we have done so far. So by 2:30 I'll give you break. So you have 30 minutes break. So by 3 o'clock we continue. So, please. Two people are shouting too much. Please. On everything we have done now, there are 96 questions here. Are you ready? Number one. Oh yeah. Number one says that a magnet is moved through a coil of wire. Are you there? A magnet is moved through a coil of wire. The EMF produced in the wire depends on
You went outside.
So what's the answer to number 1? So don't forget that your phi is equal to BA. But this BA can have an angle associated with it. And that angle is cos theta. So you can have it as phi is equal to BA cos theta. Is that taken? And remember that we said that E is equal to N the phi over dc. I mean, what's your d phi? That's changing this one. So you can say that's NDA cos theta over dc. But I told you that your area can just be something like length and breadth. So meaning that E can be equal to NDL over time, maybe cos theta, right? And we say distance over time is what? Velocity. And we say E can be equal to So the question now says that what are the factors? A magnet that is moved through a coil. So as you are moving the coil through the magnet, they said that the EMF it generates in the coil, in the wire, is going to depend on what? It's going to depend on number of turns, Abby? Yes. Is that correct? Yes. So option A says number of turns of the coil, yes. Option B, the strength of the magnet, that's this one. Is that taken? Yes. Then C, the speed at which the magnet is being moved. That's velocity. Shortly, that's how you attack some questions. So the answer is D, all of the above. Are you there? Number 2. On an AC generator, which of the following does not apply for an AC? Commutator. Is that taken? Yes. Number 3. The electricity from Kanji Dam is transmitted at high voltages and on the order of 100 of kilovolts, like very high voltage. But it is converted to domestic use of about 20 volts by what? Do you understand that? You can see that you understand what they are saying. So if you understand what they are saying, you will not be confused. You don't even need to see option before you know your answer. Do you get my point? So what did they use to convert it from Kanji Dam to convert it to a very high voltage? It was still transformer. But for domestic use, it has to be stepped down, and they still use what? A transformer, and that is a step down transformer. Number 4, Abby. Which of the following statements is incorrect? Which of the following statements is incorrect? The sensitivity of a galvanometer, which incorporates an optical lever. You did this as an assignment, Abby. So you tell me the answer. Which incorporates an optical lever arrangement may be increased by providing a large number of turns in the coil. So which of them is incorrect if you want to increase the sensitivity of a galvanometer? So A large number of turns is D, all of the above. E, a light source with great intensity. What will be the answer? Now, what do you want to use a light source to do in a galvanometer? Your galvanometer is an instrument. Let me just explain the basics of galvanometer. Just like what we explained the other time, understand it this way. You have a north side of the galvanometer and you have the south. Then you have the magnetic field running in this galvanometer. That's the design. Then you have a a coil or like a pointer. So this pointer can show deflection. Just like if I say this is a galvanometer, you know, I used to draw something like this. And I'll tell you that it deflects to the left or it deflects to the right. This is how it works too. So when you connect the galvanometer to source of electricity, where it will help you to detect current, maybe to the left or to the right, it's just like those basic stories. That if current is moving, then use your right hand rule. Where will it move to? But the field, we make sure that as the current is flowing in the wire, this guy can move to the left, to the right, or to the left, depending on how the current is flowing in the wire. Now, if it moves to the right, the recording can be 0, 1, 2, 3, 4, and so on there. -1, she gets 2, 3, 4. So it can read like this. To say 2 ampere, 3 ampere, 4 ampere, she gets. And if it goes like this, that means the connection is probably wrong. Then it goes in opposite direction. So, in the sense too, we have it now. When this guy, when the current is flowing, the way it's designed, it's going to have a rotation. Now, by the time it rotates, something must be able to turn it back to 0. You know, when you remove the current, what will happen to go back to 0? Abi? That thing that they put in order to make it go back to 0 is a spring. So after it has moved like this, then the spring, when you remove the current, the spring will snap it back inside the galvanometer. That's how they design it. So that spring is what provides what we call the torsor, or I don't know how to spell that, like torsional control. So like, you know, from something that looks like tension, restoring force is what we are talking about. So the spring is what will snap when this guy, if this guy moves, you know, it will stretch the spring. There's a way it's designed so that the angle is covering balances what is happening to the spring. So when it turns like this, the spring can snap it back. Then it will cover a particular angle. Then that angle it covers, or that angle it deflects. There are two different angles. So then we now say that the sensitivity of that guy is equal to the angle divided by the current. So this is the formula for sensitivity of a galvanometer. But we now said something. We said your galvanometer, your moving coil, we now have two types. We have different. We have your moving coil galvanometer, Eddy, and your moving iron. What's the advantage and what's the difference? The first difference is the scale. Which one of them has a uniform scale? Moving coil has a uniform scale. But moving iron does not have a uniform scale. But another thing is that moving coil only measures what? DC. It only measures DC. But your moving iron measures both AC and DC. That's the assignment I gave you. So now that I'm talking about it again, I did your assignment. It will be clearer and better. So, which means that option A says that the number of turns in the coil, so depending on what the coil is, there's a coil. So the number of turns determines how sensitive it will be. Abi? So that's correct. Then the suspension that will bring it back to its position. Option B, that's also correct. Then option C, permanent magnets. Abi? That's also there. That's also correct. Then option D, all of the above. Then he is now saying light intensity from a greater. Then is there anything like lights that I've talked about here? So that's wrong. Is that taking? So number 5. Which of the following statements is correct? The magnetized states of an iron bar can be destroyed completely by what? Heating the bar to high temperature, breaking the bar, connecting opposite pole, or placing the bar. So the answer is option A, Abi, heating the bar magnet. Do we all understand that? Number 6. The figure shows a current I flowing in a copper wire situated in the magnetic field. You can see the way the magnetic field runs, Abby. So there's a copper wire base there, and current is flowing as indicated. Which of the following statements is correct? A. The wire will experience a force in the direction into the paper. Is that correct? Yes. Which of the rules will you use in this case? Because some of you are saying Fleming's right hand. When current is flowing in the wire, it is current. The other one we did, we are moving magnets. We want to know the direction of current. Now we want to know the direction of the coil now when current is flowing. So we use our Fleming's left hand rule. That was the one we did. When we use coil effect, that's what I said you should also do. DC motor and AC motor, electric motor, how fan is working is what they are showing you here. So now you use Fleming's left hand rule. So they now said that you should tell them in what direction do you think the coil will go. A, the wire will experience a force in the direction into the paper. B, the wire will experience a force in the direction out of the paper. C, the wire will vibrate in the direction into and out of the paper. D, the wire will not direction. You shall know your answer is between A and B. Abby? Oh yeah, let's check. So this represents your field, Abby. This represents the current and this represents the force. How is the field going? This way. Abby? Like this. But current is going where? Oh. So where is my thumb pointing? Inside the paper. So the answer is option A. Do you get that? So if you use your Fleming's left hand rule, it will be inside the paper. Now, back EMF can be generated here because as the coil is moving, there will be current induced. And that induced current wants to stop the motion of that coil. And that induced current is what we call induced EMF, and which is what we call back EMF. So as that coil is rotating as a result of motion of the current, there is an induced EMF. That induced EMF wants to stop the coil from rotating. Number 7. On which of the following is the operation of a moving coil galvanometer based? So the application of force on the current carrying. We ask you most of these questions during your exam, either your mock or either the main exam. They will ask you to practice. Number 8. A magnet is similar to a bipolar charge system in that a magnet is not and sounds, Abby. Then a bipolar charge system is positive. So they are now saying that both of them are similar in what way? A, it consists of two opposite poles, the north and south pole. Abby, that's still correct. B, the Earth's magnetic field has a south pole near the geographical north pole and the north pole near the geographical south pole. The Earth's magnetic field has a south pole near the geographical north pole. Is it the one that is not correct? Okay. Then let's check through the options first to see. Because that statement is correct. Option B is also correct. But the question says that this guy is similar to this guy in what way? How does B relate to what we are saying? Their similarities, does that have anything to do with option B? No. Do you get that? But that statement B is also correct. Do you get my point? Option A still looks correct for what they are saying. North and south pole, just the same way you have positive and negative poles, so they are similar. Option A looks right. But let's go on with the rest of the option. Option C, the force of attraction and repulsion between opposites and between like poles obeys the law of Coulomb's law for. Now for magnets, they said the force of attraction and repulsion between opposites and between like poles obeys the law opposites and between. The force of attraction and repulsion between opposites and between like poles obeys a law. Opposites and between, okay, obeys a law that is identical in form to Coulomb's law of electrostatic. Is that statement true? It's true. Yes. For positive charges, they repel. On like poles repel, or like poles attract. For north and north, what happened? For north and south, do you get that? So the same way charges obey this law, magnets also obey the law. Do you get that? So option C is also correct. So the answer now, option D says that A and B only. Is A and B correct? So the best answer is what? A and C only. Do you get the point there? You see why you also do not have to rush to pick answer in exam hall. Option A is correct, but you have not gone through the rest of the options. Are Obale. And Yoruba will say that Karama Bale. Karama Bale. Odoriarun. It's the highest form of disease anybody can have. You cannot be calm to think about things, to process things. You just react to everything anyhow. Then Yoruba call it, you are the one with the highest form of disease. So, the examiner too, they know how to set traps for you. And they know that if I am imbalance, no, you will fall into traps. So that's why they are saying that you look at the option A is correct. But you now quickly pick option A, then you move to the next thing because you don't want to waste time. Please, parabale. Be time conscious. As much as you are time conscious, you also have to be your answers conscious. Show you, yeah, you will be learning. Which one is best? Number 9. The name given to the characteristics, behavior of substances which sets their length perpendicular to a strong magnetic field instead of in line with it is what? Let me explain something called magnetic domain. There's white one I was using. So what is magnetic domain? All of you be getting distracted. We said something about magnets, that magnets exist as a dipole. We said if you cut a magnet into two, you will get another north and south. If you cut this again, you will still get another north and south. So that means that inside the magnet, there are several magnets. But oftentimes, that magnet knots of a magnet is usually represented by arrow. So if I just draw something like this and I say that's a magnet, this part means north, this part means south. But a magnet will not behave as a magnet if the domain is not properly arranged. It will behave as a magnet when all of the magnets are aligned in a particular direction. So a magnet can first look like this: perpendicular, scatter, blah 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 blah, or scatter. When they are scattered like this, you know, this is like north, south, north, south, north, south. At the end of the day, the way they are scattered, disarrange the magnet. So collection of all these smaller magnets, we call it magnetic domain. Magnetic domain. Now, if there's anything you can do to make sure that all of these things, this guy now, if you bring any metal close to it, it will not attract it. Because all the magnets, they have cancelled out all their effects. But you can now rearrange, and that's what you do when you are doing magnetization. If all this domain aligns like this in a particular direction, all parallel to each other, then you have what we call a magnet. Then this can behave properly like a magnet. And anything that has the ability to attract another, we usually call it paramagnet. A stronger magnet is called ferromagnet. While the ones that cannot be attracted is called diamagnet. So from what the question is now saying in its description, that the name given to the characteristics behavior of substances which sets their length perpendicular to strong magnetic field instead of in line with it is what? So if you look at all these arrangements now, the way the magnets have been arranged, they are in perpendicular fashion, compared to these ones that are parallel to each other. So the best answer is what? They are magnetism, not ferromagnetic or... Please, is that taken? So the collection of all these smaller magnets, we call it magnetic domain. Oh yeah, number 10. Come and analyze number 10. If a current is passed down the wire, in which direction will the wire move? Is it towards the observer?
Yes.
Away from the observer? Or what's the answer? So you have your north pole, you have your south pole, and you have the wire, and you have the field. So which of the rules are we using? Left is left hand. The current is down, the field is this way, then the force is out. So if you are observing, the force will be coming towards you. Okay, again. So the force is down, so the current will be down, and the field is. Are we okay? Number 11. The best material core for the core of the primary and secondary coils of an induction coil is what? Soft iron. Abi? Yes. You know, soft iron has what we call an electromagnet. Abi? An electromagnet is something that quickly gets magnetized and what? And demagnetized. Is that taken? Yes. So the answer is soft iron because it quickly gets magnetized and it quickly loses its magnetism. Number 12. Which of the following elements are real magnetic materials? What's the answer? So I told you that we have magnetic substances and non-magnetic substances. Sabi? So that's iron, steel, and nickel. Which of the following is not directly associated with direct currents? Directly associated with direct currents. A, dry cell. You have done current electricity. DC is directly related. Which other one? DC is directly related. Which other one? A moving coil galvanometer. Is it directly related? Yes. Yes. What's the function of a moving coil galvanometer? To detect current. And we said something that it measures what? Direct current. Only moving iron will measure what? AC and DC. I hope you are following. Yes. Option C, transformer. Let's look at the rest of the options. Transformer, if you think about all the working mechanisms of transformer, from all the principles I explained and the way I explained it, did you see anything like a DC here? No. You know, when I wanted to do the primary, I started with an AC source, Abi. Yes. And the AC source, why? Because we wanted to be changing the field. So that as the current is flowing this way, the field is alternating too. Then we relate it by mutual inductance. Then we generate potential. So which means transformer is directly related to AC, not DC. But let's look at other option. Option C, option D, lead acid accumulator. That is also DC. That's a battery. That's the battery you have in your car. Abi? Sorry, you don't have a car. What is do you have a car? Yes. Okay, let's get this Benz. Option E is what? Commutator. Commutator is directly related to DC, yes. Because it's the one that makes the current to only go in one direction. I'm understanding. Which one is next? Number 14. A transformer has 300 tons of wire in the primary coil and 30 tons in the secondary coil. If the input voltage is 100 volts, what will be the output voltage? Now, let me ask you a question. Olinda, without solving this, stand up. Stand up. Without solving it, the value of the voltage you are going to get, should it be higher or lower? I'm not giving you time to discuss it. The value of the voltage you are going to get, should it be higher or lower? Lower. So let's look at it. Everybody, they said you stand up. What's your name? Yes, so to it's a new name. What's your name? Musumolaje. Toluwalaje. Tigers. That's the name of my team. Now, she said that the voltage the value of the voltage should be lower. You are smart, you are handsome, you are dark, you are tall, you are beautiful. We are saying something. Yeah? Speak with confidence. It's obvious that the number of turns in primary is more than the number of turns in secondary, so you are expected to have a greater value. Let's now imagine that day in the example, God forbid, your calculator is not working and you don't know how to solve without using calculator. Look at all the options. Which options would you have eliminated? All the values are below 30. So all the options are below 30. So you cannot eliminate anything. You have to solve it, whether you like it or not. But in such case scenario, let's say two options have values that are higher and two options have values that are lower. Then that means you first eliminate those two that are higher. Then if there is no time, you can quickly pick one out of the remaining two. Do you get that? All these are part of exam logics at times that you apply to do well. You can have your seats. Thank you. So what's the answer? 10? So 10 votes. So you would have known. Number 15. Are you all there? No. Yes. We should solve your work. You know last time. So we have just know that whatever is the same except for the current. So you can say ES over EP is equal. You can say ES over NS is equal to EP over. Where is marvelous? Where is he? What did he say? He has a plan for today. So where is the question? Number 14. The transformer has 200 tons, and they might not tell you if it is primary or secondary. That's why understanding principle matters. They might not tell you. They might just tell that a transformer has an input number of tons, 300. The moment you hear input, you already know that's your primary. Shake it. So you already have your number of tons of primary. That's 300. Then and 30 tons in the secondary. So number of tons in secondary, 30. If the output voltage is, look at that word now, output voltage. What does that tell you? Secondary voltage. Then times. So you are looking for EP.